In the last section, we talked about sampling distribution of the proportion, and we used this example where we're drawing from a population that has an expectation of 50% males. So we see this example here. Oops, let me grab my pen here. And we found that the z-score were over 4 standard errors from to the left of the mean. When we shift the population, so now we're drawing from a population that has an expected proportion of 35% females. Well, in this case, our z-score now drops to 1.3. And this figure kind of shows what we're seeing. When we expect 50% males, we can see that 28% is a long ways from the expectation of 50%. But when we shift that 50% expectation to what is more likely to be the pool of applicants for a business program or an MBA program, that same 0.28% is only a little over 1 standard error away from the mean. So it's important to understand what the expectation or the population proportion that we're drawing from. Now, as a slight variation, and you're going to get the same answers as you did before, we can look at this normal distribution as an approximation to a binomial distribution. Now, we don't really cover binomial distributions much in this class, but I only present this to you because sometimes you'll see these standard error of proportions presented simultaneously, and they're calculated just a little bit different. Where rather than looking at a proportion, we're looking at a mean or an expected mean, which is simply the sample size times the expected proportion. When we do that, we have to calculate the standard deviation or the standard error of the proportion a little bit differently. We take the the sample size times pi times q. Pi is the probability of a binomial event or the expected proportion of the population. Q is just 1 minus pi. So this goes into our denominator for our z-score. This now goes to our numerator for our z-score. And now we would say, okay, we have 44, we expect 44 females in a sample of 88. Well, 28% of 88 is only 25 females. So we got 25, we expected 44, and the standard error of the proportion or standard deviation of the proportion of a binomial is 4.69. Notice that our standard errors are identical, and taken to a normal distribution table, we get the same probability of getting 25 females out of a class of 88, where we expected 44 females out of a class of 88. So this is the same probability as presented using the proportion rather than the outcome. Both conclude that the probability of a randomly selecting only 25 females from the general population is really quite improbable. Less than 1/100th of 1%. Now let's use those same calculations and look at the second example. So in this case, we don't expect 44. We expect 30.8 because our population proportion, or the pool of candidates that we're drawing from, is now 0.35. And 0.35 times 88 gives us 30.8. So we'd expect 30.8 females out of a class of 88, not 44. Well, we still only have 25 females out of that class, divided by the standard error of the proportion. Notice that that changes just a little bit. And the reason that changes is because our pi, or expected proportion of the population, changes. So it changes from 0.5 to 0.35. 1 minus that value is 0.65. We find that we are 1.296 standard errors or just under 10%. Now, this is slightly different than what we saw in the previous problem. And you've got to remember that it is just an approximation of a normal distribution. Either way, you can use either way in this course, recognizing that what we're doing is we're taking a distribution that is very non-normal, a dichotomous or binomial distribution, male-female, and we're making an assumption that if the sample size is large enough that we can assume a normal distribution. Both cases we find that the similar decision that it's much more probable of getting 25 females when we expected 38.8 than it would have been if we got 25 females when we expected 44.